In this particular lesson, this unit one lesson, we want to look at a thing what we call harmonic motion, and you're going to hear us use the term simple harmonic motion, right? Now, as you're seeing on the screen, simple harmonic motion is motion, or harmonic motion, I should say, is motion that repeats itself. In other words, oscillate about an equilibrium position. Now, we have been talking about different types of motion. We talked about linear motion, we talked about projectile motion, circular motion, gravitational motion, and that all has to do with how things are actually moving. Now, we want to spend some time to deal with harmonic motion. It's under module 2 of the CAPE syllabus, unit 1, right? And in this particular lesson, we're going to explore um, how pendulums actually work, right? Meaning that for something to undergo simple harmonic motion, there are specific things that have to occur, and we can use a pendulum to represent or to express simple harmonic motion. Similarly, when a spring has been displaced, right, from its equilibrium position, we are able to capture that movement using a graph, and based on this, it's oscillating, meaning that it's going up and down, right? So we're going to look at a few of those things in this lesson, right? We're going to talk about the pendulum, we're going to talk about springs and how springs work, and all of those kind of things, all right? But before we jump straight into the whole lesson of simple harmonic motion, there are certain terminologies that we must become acquainted with. One of those is um, displacement, right? A displacement, the symbol for displacement in some cases will use X. Well, in most cases we'll use X for the displacement, and that's just the distance from the equilibrium position. Okay? Right? We soon explore what we mean by equilibrium position, but in essence, equilibrium position just speaks to the starting point. So let's imagine that, for argument's sake, that you have a pendulum and the pendulum is positioned here, right? A pendulum would generally hang vertically downwards. The position where the pendulum is in without being disturbed is what we call the equilibrium position. Now, the very moment we take this pendulum and bring it over to the right, we say it now has a displacement. And that displacement is a distance away from the equilibrium position. So that distance along the x-axis will tell you what the displacement is. All right. So up to this point right here, this would have been your displacement on your x-axis. Okay. All right. And of course, typically with a pendulum, it's going to come to this point, right? It's going to stop, and then it's going to come back on this side. We'll soon talk about what happens when it comes back on that side. Now, another terminology that we want to talk about is what we call the amplitude, right? And the symbol for amplitude is capital A, and it tells us that the amplitude, right, is the maximum displacement. So when we look at a pendulum, if we look at this diagram right here, somewhere right here would have been the amplitude, because this is where the pendulum stops, right? So that is what we would call the maximum amplitude. It's the furthest distance that the pendulum will go once it has been displaced. right, from the equilibrium position. So that's what we call the amplitude. So if we look at this diagram here, at that location, that would have been um, one of your amplitude. This would be one of your amplitude, right? This side is going to be another amplitude. So there are two amplitudes, um, or there are two maximum displacement that you can have, as you can imagine. Once you displace it from its equilibrium position, it's going to move up to a point. That displacement is now what we call the amplitude. Then it's going to return through the equilibrium position, and then it's going to attain another amplitude, which in most cases will be the same value as this one. However, on this side, you would classify this side as being the positive side, and on this side being the negative side. So when you think about a typical displacement versus time graph, displacement versus time graph. So time is on my x-axis, and displacement x is on my y-axis. Now, if I am displacing my object from the equilibrium position and it is moving towards the right, then this is what I would see at first. Then when it reaches to its maximum amplitude, right, that object is now going to fall, right, comes back to equilibrium position, which is this line right here, which means that you're at zero displacement from the equilibrium position. Then you pass through the equilibrium position, and then you attain another amplitude, which is in the negative portion over this side, right? And then it comes to the maximum amplitude, and then it goes back to the equilibrium position. So that is what is taking place as the pendulum oscillates back and forth, right? So one side has a positive amplitude, the next side has a negative amplitude, right? And as you can see, this portion is speaking about when the pendulum has passed through the equilibrium position and now ventures into the other side of the pendulum system, right? So you have two amplitudes, as I would have stated, and the amplitude is the maximum displacement from the equilibrium position, right? And as I said, in most cases they are the same value. So if this amplitude on the positive side is 10, on the negative side it's still going to be 10, but we use a negative to just show that there's a change in direction. As you can imagine, we're talking about simple harmonic motion, right? A terminology that is going to come into play is what we call period. You have heard about period already in circular motion. In circular motion, it's the same definition, right? It says that the period, capital T, is the time taken to complete one full oscillation. Now, you might be wondering, what is one full oscillation, right? A complete oscillation can be taken from different angles. However, I'm going to take it from this standpoint. So let me erase some of what I have on the board right there, and let you understand what we mean by a full oscillation using simple harmonic motion. So when we consider the pendulum again, right? When we consider the pendulum, let's imagine that this is the maximum amplitude on that side, and on this side, this is the maximum amplitude. Okay? Now, this is my starting point. Let's call it the starting point, number one. That's my starting point. Okay? Then my pendulum has been displaced to this side, right? This position is now 2, all right? right? So this we call this position 2. Now, as you can imagine, our pendulum is going to return to 1. It's going to return to position 1. Going to return to position 1. Sorry about that. Going to return to position 1. And when it returns to position 1, let's call it position 3. It's going to pass through position 3. It passes through, well, it passes from position 1 to position 3. Then from position 3 back to 1. Then that is when we classify one time period. So that, as a matter of fact, that is what you would call one oscillation. So one oscillation is basically when, I don't want to say when the system has returned the equilibrium position, because as you could see right here, when you displace it from this position, right, it went up to number 2, then from number 2 to back to 1, and then from 1 to 3, and then from 3 back to 1. That is when you would have one full oscillation. It can be a tricky thing to understand because you would hear them say that one full oscillation is when the pendulum reaches back to the equilibrium position. But in our case, it's when depending on where you start. So if you start at the equilibrium position, it's when the pendulum has basically passed through the equilibrium position twice. So the first time it would have passed through the equilibrium position, it's when it's moving from 2 back to 1, and when it is moving from 3 back to 1. Right? So that would have been the second time that it would have passed or arrived at the equilibrium position. Now we can look at it from another standpoint. So let's draw another diagram. Right? Let's suppose that this is where I start. This is now number 1. Right? Let's call it number 2, and then now this position 3. All right? We're looking at when we say we have a full oscillation. That's what we are really doing here. This is where I start. All right? This is a little bit more easier to understand. So in this case, a full oscillation is when the pendulum would return back to number 1 after being displaced from number 1. So number 1 is your starting point. That's your starting point. For us to consider one full oscillation, your starting point must be your end point. So you would expect that the pendulum is going to move from 1 to 2 because you're starting at this position. It's going to move from 2 to 3, right? Then from 3 back to 2. Then now from 2 back to 1. So this would be one full oscillation. Oscillation when you displace the object from maximum amplitude, right? That's when you displace the object from maximum amplitude. And similar thing would happen if you displace it from position 3. So if you were displacing it from here, your full oscillation, it would be when the object moves through the equilibrium position, goes over this side, and then come back to 3. That's what we call one full oscillation. Now, another terminology that we'll talk about is the frequency, right? The frequency, and the frequency speaks to the time, the number of oscillations per unit time, right? And of course, you will see us using this formula that says You have been using it already, by the way. That says t is equal to 1 upon f. So if you want to find f, f is equal to 1 upon t. 1 upon t. All right. There are other equations related to that where we would say number of oscillations per unit time. So what if the number of oscillations is n, which means that you would have counted the number of oscillations, maybe 20 oscillations, right? That 20 divided by the time taken to complete that 20 oscillation will determine and tell you the frequency, right? So yeah, so that's what we classify as a frequency. Now, as it relates to simple harmonic motion, right? There are certain things that we we have to remember as it pertains to when something is undergoing simple harmonic motion. As we would have stated earlier, that harmonic motion is motion that moves back and forth, or in other words, oscillates, right? So once you can identify something in nature that oscillates, right, then you can apply what we call the whole concept of simple harmonic motion to it. Okay? So it says that simple harmonic motion is a type of oscillation where the acceleration of the accelerator is directly proportional to the displacement from the equilibrium position and acts towards the equilibrium position. It says that the key equation for simple harmonic motion is this, meaning that anything that is undergoing simple harmonic motion, this equation here is one that must hold true. It must hold true based on what simple harmonic motion is defined as. So SHM, simple harmonic motion, for the acceleration, we say that the acceleration is directly proportional to the displacement, right? What we mean by that, the further away you displace the pendulum. So let's imagine we have two pendulums here. So we have a very small pendulum, right? And you displaced it right here. That's the displacement. Now, because this displacement is called displacement x, right? It's a very small displacement. We are literally saying that the acceleration that the pendulum is going to have, right, is going to be directly proportional to x. However, what if we had displaced the thing now at a distance from the equilibrium position as 2x? What if we had 2x? Then it means that our acceleration is going to be twice as much from when it was at a displacement of x. So there is a directly proportional relationship going on there. So the further away you displace the object from the equilibrium position, it's the more acceleration that's going to have. Now, as it relates to this minus sign, that minus sign is telling us that the acceleration is always directed towards the center. Not only that, but it is telling us that the acceleration is moving in an opposite direction than the displacement. And I think I will show you that in a few, right? As we know, displacement is a vector quantity. Displacement is a vector quantity. It's a vector quantity, all right? So let's look at this now. So we have a system here that has been displaced, right? This is the equilibrium position. Equilibrium position. Now, as you can imagine, let's see if we can just draw a Cartesian plane right here. Now, from equilibrium position to where the object is, as you could see, this is going in that direction, meaning that um, it's moving from basically left to right, or it's moving towards the right. That's how your displacement is positioned. I shouldn't write this. Let me give me a second here. Um, yeah, yeah. So your displacement clearly is going to be going in that direction, meaning that that's how you would measure your displacement. Now, as it relates to the acceleration, right? Your acceleration is always directed towards the center, meaning that it's a vector quantity that is always directing towards the center, meaning that it is the acceleration that we're talking about is somewhat of somewhat what we call a centripetal acceleration in a sense, because it's always pointing towards the center. As you can see, based on comparing this, your displacement is going towards the right, and your acceleration is going towards the left. So hence that's the reason why we have a minus sign to just show you that the acceleration is always acting towards the equilibrium position and is in the opposite direction, right, of the displacement, right? So when you displace the object, right, you realize that once the object reaches its maximum displacement, then you're going to realize that the acceleration is going to be directed towards the center. Okay, so that's the rule of thumb um, when we're dealing with simple harmonic motion. It says here that the negative sign is used to show the direction of the acceleration is always towards the equilibrium position in the opposite direction to the displacement. Okay, so just remember this equation that says the acceleration is equal to negative omega squared times x. That's how we find the acceleration in a in a system that has simple harmonic motion taking place, some type of oscillation taking place. You would use this equation to find the acceleration of the system. Here are some conditions that are necessary for simple harmonic motion, and you would have heard about them previously. We must know how to state these conditions. It says that an object experiencing simple harmonic motion, when it accelerates, when its acceleration rather is directly proportional to the displacement, right? And the acceleration is always in the direction, in the opposite direction to the displacement from the equilibrium position. So that's the rule of thumb. Those are the conditions that are necessary. So if those are not, if you're not seeing those things taking place, then it means therefore that the system is not undergoing simple harmonic motion, right? Yeah. I must let you know that for the system, for a simple harmonic, let's take for example a pendulum. For the pendulum to oscillate, you have to displace the pendulum from this position, meaning you have to displace it from maximum amplitude. You can't displace it from equilibrium because you would have to move the string, as you can imagine. You would have to move the pendulum up to some distance, and then you let it go, right, for it to oscillate. And I'm thinking that you guys probably have used a pendulum before or oscillate a pendulum before. You have to pull it just like a swing song, right? You would generally allow somebody to pull you up in the air and then let you go for you to can oscillate. All right. So as you can imagine, you would have been displaced, right, from the equilibrium position, and then you would have been held here for a little bit period of time at the maximum amplitude. Then once you are let go, then you realize now that your acceleration is towards the center, right? Towards the center, coming down. So that's what we mean, per se. Here are some examples of system which undergoes what we call free oscillation. Now, free oscillation is when a system oscillates, uh, and let me see. Free oscillation. It would seem as though free oscillation speaks to when a system oscillates, you know, by itself, providing that there is no frictional forces that are there. All right, because obviously if there are frictional forces, then it might not be completely free oscillation. All right, but these are some examples as to what free oscillation speaks to. It says that a simple pendulum is an example where you have a small dense bob. The bob is like the small metal ball that is attached to the string, right? That hangs hangs from a string, which is attached to a fixed point. We've been looking at pendulums so far. It says once the bob is displaced and let go, it will oscillate freely. So it means that nothing will stop it from, well, something will stop it eventually, but it oscillates by itself. That's what you would generally call free oscillation. All right. A mass spring system, that is the a spring attached to a mass. When you pull the mass down, then you would expect that the spring is going to compress and retract and all of that kind of thing, right? Yeah. So that's a type of free oscillation. There's a thing what we call a tuning fork, right? And you can go ahead and research it as well. But a tuning fork looks something like this. It looks something like this, where it is able to produce vibration, meaning that sound, it's able to produce sounds, where by knocking or by striking this part, you'd expect that sound waves would be emitted. Now, those sound waves are actually oscillating, because what you would realize is that you will hear it at a very high pitch, then at a very low pitch, then at a very high pitch, low, high. So that would speak to it being oscillating sound waves right there and then. Now, as you know, whenever we're dealing with um, any type of motion, there is some type of speed involved and all kind of thing of that nature. In this case, the speed that we'll be dealing with, or the motion that we'll be dealing with, is angular velocity, or in some case you'll hear us saying angular frequency, right? So if you see angular frequency, it's the same thing as what we call the angular velocity. It's nothing new to us, because the symbol for angular velocity and angular frequency is omega, right? It says that similar to when we were looking at uniform circular motion, and we went ahead and calculated the angular velocity, right? It's the same way how we would calculate it whenever we're dealing with simple harmonic motion, where we said that angular velocity is equal to 2 pi radians divided by the period, or we could say omega is equal to 2 pi f, where f is the frequency. Now it says recall that angular frequency or angular velocity is the rate of change of angular position, where this is your angular position divided by t. Okay, so that's just what we're recalling there. Let's move into a little thing here now. When it comes on to simple harmonic motion, right, we're going to realize that there are different graphs that we will be talking about, right? And we just have to know where the object is being displaced from. So if the object is being displaced from equilibrium, there's a specific graph that is used, so to speak, to represent the displacement. Also, if an object is displaced from its maximum amplitude, which you could classify to be in here, so if this is your maximum amplitude, there is a specific graph and there is a specific equation that would tell us that the object has been displaced from the maximum amplitude. All right. Now the proof can be a little bit daunting, and I don't think we necessarily need to know the proof, but the equations, we must know the equations, or and not only the equation, but we must know the graph that corresponds to the equation. All right. So we're going to look into that a little bit. All right. Firstly, we could derive the first one. We could derive the first one. All right. Now let's imagine this is a typical view of how the pendulum looks. Right. This is a typical view. What if we were to look at it from this standpoint? If we were to look at it from this standpoint, it's the same thing, meaning that the object has been displaced from its equilibrium position. So let's imagine that this is the equilibrium position. It has been displaced to some distance here. So you could call this your amplitude. If this is your amplitude, right? Now, mind you that there is an angle in between here that we're going to call the angular displacement. All right? This is your angular displacement. Now, by way of applying some amount of resolving of vectors, remember that displacement is a vector quantity. So if displacement is a vector quantity, it means therefore that it has horizontal and vertical components. Because we are interested in the displacement along the horizontal axis, it means that if we were to make a triangle, a right angle triangle in between here, this side of the triangle right here would represent our displacement, or in essence our horizontal component of the displacement, which is what we really want, because displacement is always along the x-axis. As you can rightfully see here, it's along the x-axis. All right, and we want to denote that. Mind you that the angle is positioned here. The angle is positioned here. So if the angle is positioned here and you have a right angle triangle, it means that this side is going to be your adjacent. All right, so that side is your adjacent, and we know that adjacent in trig ratio, the more appropriate trig ratio to use in this case would have been cos of the angle equal adjacent divided by the hypotenuse, where your hypotenuse is A, right? Which is the hypotenuse here is A, capital A, which is the maximum amplitude. Remember that is that is the vector that we're trying to resolve. So your hypotenuse is A. So we want to just rearrange this equation. We said that hypotenuse is A. We want to get the adjacent side. By way of just transposing, you're going to realize that A cos theta is equal to the adjacent. So your adjacent side, as you can rightfully see here, is A cos theta. Good. But there is something that you can recall. So now that you know that side is the displacement. Then you could say now x, your x displacement is equal to A cos theta, of course. But recall that theta divided by t is equal to omega. We want to substitute theta. So theta is equal to omega times t. So x now is equal to A cos omega t. This equation is an equation that tells us the displacement when the object is displaced from the amplitude. So if the object is displaced from the amplitude, then this would have been the equation that we would have used, right, to, or this is what the displacement would have represented when we have the thing starting from the amplitude. That's one equation. Now there's a specific way how a cos graph looks, right? But before we talk about the cos graph, the sine curve or the sine graph is a graph that starts from zero, which means it starts from the equilibrium position. So if your pendulum had been displaced from zero or from the equilibrium position, then you would essentially see the object going up. You'd see the object going up from that equilibrium position, oscillate all the way up to the amplitude, come back down, back to the equilibrium position, then back to the next amplitude on the other side, and obviously come back to equilibrium position where you would have completed one time period. Agree? So this here, this graph is showing us the displacement x when you are starting from zero. Okay? That's when you're starting from zero. Mind you, this right here is your amplitude. That's your amplitude. Alright? Now, if you've seen x naught also represents the amplitude. Good? This type of graph is obviously a displacement versus time graph. So once the object has been displaced from the equilibrium position, then the graph that you would represent or you'd use to represent the displacement is a sine graph. If you're paying attention to the notes here, it shows us that sine version of the equation is used if the oscillator begins at the equilibrium position. And then now for the cost version, it says that it is used if the oscillation begins at the amplitude position. As I would have been showing you around here to say that if you had to begin at the amplitude, if the oscillation had started at the maximum amplitude, or the amplitude I should say, then the equation that you would use is a cost equation, which has a specific way how it looks, right? We're going to look at that. Well, I should have had it here, but it's not there. But I'll draw it and show you what it looks like, right? As it relates to the cost graph. And I think you can imagine that you have your graph looking like this. This is your amplitude. So you have one amplitude on this side. Come on, think, baby. Then you have your negative amplitude on that side. Now, if you're starting from the amplitude, meaning that you're displacing the object from the amplitude, you would expect that your graph is going to start right here. It's going to start like this. It's going to come down to the equilibrium position. Then it's going to go down to the second amplitude and it comes back up. And it continues like this. Mind you, this side is going to be time. This side is what we call a displacement. So this side is a displacement. Right, displacement. So this is a displacement versus time graph for when the object is displaced from the amplitude. So you displace the object from the amplitude. You would expect a graph looking like this. Now this type of graph, whenever you have a graph starting at the amplitude or starting right here, right? Then that graph is what we call a cost graph. The cost, a cosine graph. It's a cosine graph. It's a cosine graph. It's a cosine graph, and hence this is the reason why this equation now would work for this type of graph, because or it will represent it much better. So once you're seeing the thing starting here, right, then it's a cost graph. Once you see the graph starting here, then this is a sine graph. All right. Now in just the same way, we can derive an equation for the velocity of the object that is oscillating, right? There's a specific equation that we use as well to represent the graph for the velocity of the moving object or of the pendulum. All right. When we look at it, these are the graphs that are used to represent that. So here we have another cost graph. All right, we have another cost graph right here. So if you have a cost graph, then what this tells us, it tells us that we're starting at the amplitude, right? We're starting at the maximum displacement, the amplitude, and then you are progressing downwards, all of that kind of thing. All right. Here we also have another graph here where this one is showing us also that with this graph, you see, this graph is, I must say something here. For this particular graph, it's not when you're starting, yes, it might look like you're starting at the amplitude, but it's not necessarily at the, yes, this one is for when you're starting at the amplitude, definitely. This is one for when you're starting at the amplitude, all right? This one here is for when you're starting at the equilibrium position for the velocity, okay? So let's imagine displacing the object from equilibrium position. You displace the object from equilibrium position, you would expect yeah, let me see something here. Give me a second. All right. Yes. So there's a clarification. I think I'll use this to kind of explain it a little bit. All right. Um, there's a little bit of a switch or a trick to this thing here. When we displace an object from equilibrium position, all right, and it's oscillating, an object is oscillating and all of that. When it comes on to the velocity graph, when we're at or when we're starting the graph, right, we're literally saying that at the equilibrium position, that is when you would have the maximum velocity. That's when you would have the maximum velocity. All right. So in this case, we we are using a cost graph to represent that information, where your maximum velocity, v is equal to the amplitude times omega, or you could say v is equal to x naught times omega. All right. So let's look at it. Whenever we're starting our displacement from equilibrium position, right, what you would observe later on is that when the object is passing back through the equilibrium position, that is when the object is going to have its maximum velocity. If you can think back about transfer of kinetic and potential energy in a system. So if the system is oscillating, let's imagine that you're oscillating a pendulum, right? You know that at this position, at the maximum amplitude, or you should know that at the maximum amplitude, that is when you're going to have maximum potential energy. But once you now reach the equilibrium position, you're going to have maximum kinetic energy at that point, which just shows that the speed is maximum, or the velocity is at its maximum. It's at its maximum. Hence, this is the reason why we're saying that when an object is passing through the equilibrium position for a sine graph, right, we can say that it's going to have its maximum velocity at the equilibrium when it's passing through the equilibrium position. All right, that's really how it works. When the object is at the amplitude, when the object is at the amplitude for a sine graph, right? That is when it's going to have its lowest, or it's going to have um, zero velocity, because at the maximum amplitude you would expect for an oscillating system, it's going to come to a stop at the maximum amplitude, which just tells us that there will be no velocity for a period of time. Then that velocity is going to then decrease, and then now um, reach to zero. Well, not reach to zero, but reach back to the maximum. Reach back to maximum again. So let's imagine here that you have the object coming to the maximum amplitude. Once the object reaches the maximum amplitude, it's going to come to a stop, which tells us that the velocity is going to go to zero. Then it starts to oscillate again all the way down to um, its maximum velocity. And of course, when you match it up on the displacement graph, that is when the object is passing through the equilibrium position. All right. So it's a little bit tricky to understand, but it's just for us to hopefully we got it a while ago pertaining to what is happening at different strategic locations related to the displacement and the velocity. All right. So it's best when we compare the graphs together in a sense. It's best if we only compare the graphs together, because that now kind of make it a little bit easier for us when we're looking at what is happening. All right. But there are two equations that we can use to represent a velocity time graph. You can use a cos equation, and you can use a sine graph as well. Right? You can use a sine graph to represent what is happening. Okay? You could just imagine now this graph right here. This particular graph is going to be related to when the object starts at the amplitude. Reason being, if the object is starting at the amplitude, you would expect it to have zero velocity. But as soon as the object has been displaced, right, that object is going to pass through the equilibrium position. When it is passing through the equilibrium position, this is how the velocity looks. The velocity is going to be at its maximum, right? And then it's going to come back to the amplitude for the displacement graph. And I'm going to compare it and show you as to what I mean by that using the next set of graphs. So whenever we have a cost graph, cost displacement graph, we said that that is when you start at the amplitude. Your displacement starts at the amplitude. Now, as I would have been pointing out to you just now, that at the amplitude, your velocity is at zero. All right? So you would expect that this is how your graph is going to progress, yeah, right? Yes, and what we can also see here is that there's a negative sign associated with this equation. This negative sign just shows us that the velocity is going towards the equilibrium position. This negative sign, the negative sign shows us that the velocity is directed towards the equilibrium position. All right. That's what the negative sign in this case tells us. It just tells us that the acceleration, not the, well, the velocity rather, is directed towards the equilibrium position. Okay. Now we're going to pick up this lesson. Then I want to pick up this lesson. We're going to talk about the acceleration, right? So just stay tuned. Okay. I want to pick up this lesson some other time pertaining and then talk about the acceleration.